Fine. Everything is good, right? You're all ready? Or not ready? So something is displayed on the screen. What is that? I'm going to ask you the questions today. Today will be only I'm going to ask you a question. You need to answer me. What is there on the board? Truth table for 2-bit comparator, right? So did you understand that truth table? Look at the truth table. Did you understand the truth table? What is that? What is P1 and P0? That is one 2-bit value, right? What is Q1 and Q0? There is another 2-bit value. You are just going to compare it. Okay. And what is that P greater than Q? It is a result, right? Result of comparison. It checks whether P is greater than Q. Can you tell me, for a combination of 0, 1 and 0, 0, you can see P greater than Q is equal to 1. Why it is like that? Why? Because of course you have P greater than 1, right? Because 1 is greater than 0. You get one entry there. And all remaining places you will have 0. So have you understood why you got that combination of zeros and ones in P greater than Q? And why it is like P equal to Q? Why P less than Q? Keep it inside, right? You know how this? You understood? Try to understand, not your mobile phone, my dear. It's very easy. Why you still understanding? It's very easy. Why you got all 0, 1, 1, 1, P less than Q? Got it right? Okay. So, what next? Tell me. I want to get a logic circuit. I want to get a logic circuit for P greater than Q, P equal to Q, P less than Q, where your P1, P0, Q1, Q0 is input. How can I proceed? Tell me. How can I proceed? Yeah, solve for P greater than Q, solve for P equal to Q, solve for P less than Q using Karnaugh map. What are you going to get from Karnaugh map? Tell me. What are you going to get from Karnaugh map? What's your name, my dear? Christina. Christina, tell me. After you just solve it using Karnaugh map, what are you going to get? No answers. You're going to get logic equations, right? You get an equation for P greater than Q. You get a logic equation for P equal to Q. You get an equation for P less than Q. How many equations you get? Tell me. 3 equations, my dear Christina. Right? And after that, what you do? Tell me. After that, what you do? My dear, what's your name? Nisha. Netra. Netra, tell me, Netra. After that, after once you get the equation? After getting the equation, according to the equation. Oh, very good. Fantastic. That's great. Right? What you do? You implement it using logic gates. That's all. Right? So ultimately, what you designed? A circuit for 2-bit comparator. See, such a great thing. You designed a hardware. How you did it? What came first? Truth table came first, right? And after that, Karnaugh map, get the equation, implement it using logic gates. Have you understood? This is called as combinational circuit. So what you did is a combinational circuit. And there are many combinational circuits exists. This is one of that. There are many. Half adder, full adder, all those things we have seen. Right? I've understood this. Okay. Now, knowing this, how can you do 4-bit comparator? How many inputs will be there? Right? How do you solve the equation? 8 input Karnaugh map. Do you know 8 input Karnaugh map? Now then how many squares will be there? See, this itself is 4 cross 4, right? When you solve your K map, this itself is 4 cross 4. Suppose if it is 4-bit comparator, 16 cross 16, right? Yes or no? 4-bit means you will have how many inputs? Tell me. 8 inputs. How many variables will be there? 8 variables. For 8 variables, Karnaugh map, what will be the size of the Karnaugh map? It is impossible. Right? That's where we use that EDA tools. That's where you use the one which you are using in laboratory. That's cadence, or if you are going for FPGA, field programmable gate array, you use that Altera Cortex. There are many. This market is huge. Okay, there are many softwares. Software market is very huge. You all know about it, right? Everything is fine now, or not fine? Good? Enjoying? Now tell me, what did you learn from doing experiments using field programmable gate array? I just want to get some feedback from you. What did you learn? That something is getting downloaded into something and you're getting the output. What did you learn? What's something you found it's very easy, or you found something difficult? What is your feedback about it? There is no test bench. Okay, then very important thing you have not told me. Very important thing which you're supposed to do in the one more lab with all wires and ICs. That is not required at all, right? That struggle is not there. I see most of the students, they struggle to connect the wires. You connect all the wires, ultimately output will not come, right? So you are using actually the basic ICs and trying to get your combinational circuit. Instead, you are using only one IC. Inside that you have an arrays of gates which you configure it, okay, for your requirement. It can be a half adder, it can be a full adder, it can be encoder. You must have seen, right? First you did half adder and you erased it. Then you did full adder. The same IC, like when you are programmed, it became half adder for you. When you programmed full adder, it became full adder for you. Yes or no? You have programmed it for encoder, it became encoder for you. Yes or no? So it's something like general purpose IC, yes or no? The field programmable gate arrays are nothing but a general purpose IC, where you program it and get your same thing here. You write a program for 4-bit comparator, you get it implemented in field programmable gate arrays. Have you understood this? And that particular general purpose IC which you are using, its capacity is something really great. You can even program it to behave like a microprocessor or microcontrollers. You can program it to behave like an AI algorithm, right? I've understood now. Hmm? The system which is working on AI, you can program that IC, you try to implement those algorithms there. That IC has enormous capacity that you program for any requirements, you make a hardware for that. Right? So there is a requirement of hardware for any software you develop. You understood what I'm trying to tell you, right? You develop on software, you are expert in software, but how do you get a hardware for that? Right? You cannot keep a PC in a car, right? You take a autonomous car, right? Self-driving car. Do you keep multiple your that big GPU, the system inside the car? It's not that. You need a developer, an integrated circuit for that. That is done using that field programmable gate arrays, but involves lots of programming in that. So what we are teaching you is simple, very simple, half adder, full adder, because it's the beginning for you. It is, you have to take your career up in that. A lot of opportunities for you. If you want to work in a good big companies like Apple or big companies, you need to develop your skills in those areas, right? Okay, right. So that's what the advantage of using that field programmable gate arrays, which we thought we'll introduce instead of you simply struggling with wires and all, because nobody in the field is you're going to do these wires and all. It's gone. That era is gone now. Understood? Okay. Okay. So this is about your lab, which I just wanted to tell you that this is what the benefit of using that. You have both software and hardware. Together you are doing it. Understood, Aditi? Everything is fine, right? Okay, good. Feel free to ask questions, doesn't matter, okay? So we have seen 2-bit comparator, 4-bit comparator. Of course, it won't come for exam, don't worry at all, right? Because it's huge task to do, right? Because you have 8 variables. So 8 variables, so how many combinations are going to come, You know that, right? You will have 16 cross 16, and you group it and all. It's impossible by hand. You need a system for that. You try to program for that. Okay. So doing this, thinking that you all know about this is what you get after solving K-map, and just put it in the form of basic gates, right? And if I ask you to write a program for this, you know it, right? You can write any, right? You can write a simple gate level model or simple data flow model, right? Okay. You know what is the equation for P greater than Q. You know what is the equation for P equal to Q. You know what is the equation for P less than Q. If you want to write a program in Verilog, you can just write it, right? Write a Verilog code for 2-bit comparator using gate level modeling. Write a Verilog code for 2-bit comparator using data flow modeling. Both you can write, right? Of course, here you may have many number of gates, right? You will have, say, G1, G2, G3, G4, G5, G6, G7, G8, G9, G10, G11, D12, G13, G14, G15, and so many wires you may have, right? Yes or no? If you know how to write a program using gate level modeling, you may have so many wires here, right? You have 1, 2, 3, 4, 5, 6, 7, 8 wires, so many wires and all you will have. But of course, you can write a program using gate level modeling. Yes or no? Yes or no? It's very easy, right? How do you write a data flow model? Data flow model is very easy, right? Just implement this. In your Verilog program, you write, give a variable for this, variable for this, variable for this. Just implement this. How can you implement this? This is P naught and not of Q1 and not of Q0, or write this equation. That's all. That's all. Have you understood? Hmm? Right? It's not difficult, right? Is it difficult? Is it difficult, Harun? Not difficult, right? Just little bit you have to practice. You know what to do, but maybe while writing you may not be able to write. That's why, write one Verilog program by yourself. Just one, enough. Have you understood what I'm trying to tell you? Right? You can do it. If you have any doubts, please feel free to come, or you will not come, I know. Right? Now, 4-bit comparator. See, 4-bit comparator, as I told you, can you write a gate level model? Huh? Tell me. Of course, it's too long. It's too long. How many lines of codes you write? Of course, Indians are very good at writing codes. They write 1,000 lines of code per day. It's not a big thing. Here and there, they will copy paste. Americans like it. They bring all Indian engineers come to US, do cut and paste, right? Fine. But writing 4-bit comparator, if you want to write a gate level modeling, you don't know how many gates are there in that. Then there may be 50 gates. Your code will be very, 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 very long. Similarly, you get 3 equations with the 8 variables as an input. Just imagine how much long equation you get. Just imagine. So will you be able to implement data flow model of that? It's a big equation, very big equation. It's not practical, right? The best thing is behavioral model, right? Just take the behavioral model. See, you just have to put these conditions. See, in 4-bit comparator, see, if A greater than B, it can be possible only when A3 is equal to 1 and B3 is equal to 0, yes or no? Right? It's the binary value once again. If A3 is equal to B3 and A2 is equal to A1 and B2 is equal to 0, you just see that, which are bits makes that number greater. If A3 is equal to B3, A2 is equal to B2 and A1 is equal to 1, B1 is equal to 1. Similarly, A3 is equal to B2, A2 is equal to B2, A1 is equal to B1, A0 is 1 and B0 is 1. Yes or no? So in these condition of your number, okay, 2 4-bit number, we can say A greater than B. Yes or no? Just think about it. Yes or no? Right? Yes or no? When A will be B, you will have 16 combinations of A and 16 combinations of B, right? It's a 4-bit number, right? Depending on the bit value, we can say this is greater than this one. So you write what model for the program? Behavioral model, which is very easy to write with these conditions. What about A less than B? What about A less than B? Reverse of that, right? Come on. Reverse of this. Come on. Reverse of this will be A less than B. Yes or no? Just think. Right? Now, what is the condition for A equal to B? Come on. Or should be equal. Right? Your B1 is equal to B1 is equal to A1 and your B3 is equal to A3, then only it is A equal to 1. A equal to B. Yes or no? A equal to B. So use these behavioral conditions and you can write behavioral model for Verilog program. That's all. If condition, that's all. If condition, just write if condition. See, I have given you 3 tasks now. What are those tasks? Write a program for, write a gate level program for 2-bit comparator, write a data flow model for 2-bit comparator, and write a behavioral model for 4-bit comparator. If somebody is interested, write the program and implement it in FPGA. It will not take more than 15 minutes if you have a program with you to implement it in FPGA. Just you have the work of assigning those pins to that FPGA IC, that's all. Try, check your output, because those questions may appear in the comprehensive examination. You will not be given the same questions. You will be given some question, you have to implement it in field programmable gate arrays. Have you understood this? Try to practice this. Have you understood what I'm trying to tell you? Right? So write the program, don't leave it. Right? You have enough time to write the program, right? If you have any doubts, please come and meet me. Right? Okay. So let's go forward now. So combinational circuits are many, it is not one. And I told you about decoder. Decoder has n inputs and 2 to the power of n outputs. Right? N inputs, 2 to the power of n outputs. Always. If there are 2 inputs, there are 4 outputs. If there are 3 inputs, there are 8 outputs. If there are 4 inputs, there are 16 outputs. It decodes. And briefly, I have told you during my last class what is a decoder. And you have done experiments also in the lab. Some of you must have done it. Those who are having lab today and tomorrow might not have done that, but some of you know what is decoder. Anybody doesn't know what is a decoder, what decoder does? Right? A particular output will go. Right? Have you understood this? Have you seen this, in this running lights, there's something running lights you can see, right? You light series of LEDs, give a feel of running light. Right? You can put a 16 running lights at the output of a decoder and continuously supply 0, 0, 0 to 1, 1, 1 as an input to the 4 to 16 line decoder. Right? Assume that there are 4 inputs, there are 16 outputs. Okay? Each 16 outputs, assume that you have connected LEDs, 16 LEDs. Right? Now, if you want to make that effect of running light in 16 LEDs, continuously supply 0, 0, 0, 0, this combination, 0, 0, 0, 1 combination, dash, 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 1, 1, 1 combination. Continuously do that. So what will happen? First, when you supply this LED will glow, other LED will be off. When the next set of input is supplied, this LED will be on, other LEDs will be off. Like that, this LED will glow one by one, one by one. And when last 16th LED is glowing, after that once again supply 0, 0, 0, 0. First you will glow. So you will have this LED one by one glowing. That's one of the simple application of a decoder, I can say. Have you understood this? Right? That's what decoder is, that's all. Right? If you want to connect 8 LEDs, how many inputs are required as an input to the decoder? 3. That's all. That's what decoder is. Have you understood this now? Okay? If you have understood decoder, okay, and this decoder has lots of applications in your microprocessors. Decoder, because it is going to enable the outputs depending on the inputs, right? I can give you an example, simple example. Just this is your 3 to 8 decoder. I have told you this during my last class. Assume there are how many inputs? 3 inputs, and how many outputs will be there? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Yes. This is connected to your light in your hall. This is connected to fan in your hall. This is connected to, okay, AC in your hall. This is connected to, you know, okay, something, washing machine. This is connected to somewhere fridge. This is connected to something, okay. All are going to be your utensils, household items. Okay, of course there will be some setup, like a relay and other things on to switch on this. Okay, now if I supply 000 here, tell me what will get on? That will get on, right? Suppose if I connect 001, what will happen now? Tell me. Your fan will be on or light will be off, right? That's what's going to happen, right? So this is the way you can control the devices using these decoders. A lot of applications are there for decoders. Okay, a lot of applications. So hope you understood what is a decoder is. What is decoder now? Right? Okay. Sometimes this output need not be active high, it can be active low also. All of you understood difference between active high and active low. I have told you in my last class. Okay. Now, yes. Decoder, I told you many things about decoder. All of you know about decoder. This is 3 to 4 line decoder. Can you look at the just a block diagram? It's written here. What is important here is truth table. Can you see the truth table? See here, when input is 0, 0, D0 will become 1, D1, D2, D3 becomes 0. You can see, right? Similarly, when input is 1, 1, D3 will become 1, others will become 0. This is for active high output. Suppose for active low output, can you tell me what way this truth table changes? This will be 0, this will be 1, 1, 1, this will be 1, this will be 0, 1, 1, just complement it, that's all. 0. This is called active low output. Active low output. The meaning of active low output is that output will be 0. Active high output will be 1 for that particular combinations of input. Hope all of you are understanding this, right? Okay, so let's now tell me how you got this. Look at that, how you got this circuit. Same thing I told you in my beginning of the class. You have the truth table, right? Get an equation for D0, get an equation for D1, get an equation for D2, get an equation for D3. Do you need K-map for this? Do you need K-map for this? No. No, right? Right. You don't need K-map for this. You can directly get it from your equation itself, from the truth table itself. When you have an equation with you, who stops you to writing a logic diagram? Nobody will stop you writing a logic diagram for that equation. Ultimately, what you got? What you got? A decoder. Can you write a Verilog program for this? You can. You did it. That's great. You did it. Fine. Okay. Extending this to 3 variables, ABC, right? 3 variables, 3 input variables. How many outputs will be there? 8 outputs. It's very easy to draw the, right? Now can tell me what is the difference between this one and this one? Accordingly, your logic diagram also will change, right? Yes or no? So see here, this is active low output, right? Now what is the equation for Q0, equation for Q1, equation for Q2, Q3? You can get it in terms of only one gate, right? This you can do it yourself. Just practice this. You will get it definitely, right? Have you understood this? Here you can make use of the max terms, max term. You know max term? Because here, in the previous one, you can use min terms. In the second case, you can use max term, right? And you get an equation for Q0, Q1, Q2 and Q3, right? Once you get a max term, you can implement it using, just take a complement of that and you can implement it using only either NAND gate or NOR gate. Practice this, okay? But it's already done, you have to practice. I'm not going to do it again, okay? Which one? Inverter. No, that is only for the NOTing, not operation. See here, you have A bar and B bar, right? Then A bar and B bar is coming from this NOT gate. It is input is given A and output is, see, this is what A bar is, that's all. See, if you want to get a bar, you need to use a NOT gate, right? Where you get A as an input and take a bar as an output. The same thing is written here. Fine, this is very important. Okay, practice this. Now, see this. What is this here? Tell me. What is this? Decoder with enable. What is this? What is enable does? See, just tell me what the enable does. Exactly, exactly. See, if you want to enable the entire 2 to 4 decoder to work as per the decoder function, you have to make your enable 1. If enable is 0, output will be don't care. Right, output will be, it is not valid output at all. See here, see the truth table. See, when the enable is 1, A0, B0, okay? Your W is 1, X is 0, Y is 0, Z is 0. That means it functions according to the decoder, right? Fine. Now similarly, when enable is 1, combination is 0, 1, it works according to the decoder function. Now when enable is 1, combination is 1, 0, it works according to the decoder function. Enable is 1, input is 1, 1, works according to the decoder function. Now when enable is 0, whatever be the input for A and B, whatever be the input for A and B, that's why it's written XX. XX means it can take any combinations. Output will be 0, 0, 0, 0. That means unless you give an enable, proper enable signal, now in this case it is going to be 1, it is not going to behave as a decoder at all. That means dead. That is the purpose of enable input to this. almost like switching on the entire chip, switching on and switching off the entire chip to be functional. That's what enable is. One important concept you have to remember, this enable can be either 1 or either 0. It need not be always 1. If enable is 0, you can see there will be a bubble here, right? So if enable is active low, that is called as active low. If enable is active low, can you tell me what changes I have to do in this truth table? What changes I have to do? All this will become 0 0 0 0, right? Yes or no? And this will become 1. All this will become 0 0, this will become 1. This is now what type of enable input? Enable input, active low enable input. When there is an active low, you will have bubble here. Then it is called as low level enable. Low level enable. Have you understood this? Okay? There's nothing special in this. This is just. Can you look at this? What is this actually? Tell me. What is this? A program. What is a model? Data flow model of a 2 to 4 line decoder. Right. But what is extra included here? Enable. See, enable. And of, not of E. So whenever actually you just do it active low enable. Suppose if you want to have active high enable, what are the changes you have to do in this program? You remove this all not. It is active high. Active high. These are the things, very important things. Okay. So now all of you just give your attendance